All right, so we're going to want to find areas of these polar graphs. So, just like our cardioid, something like this, right? So you can tell we're not going to be able to use rectangles because that's not going to go top to bottom. So what we're going to need to do is make sectors. So these are like pieces of a pie, and these pieces of the pie will always start from the origin. So this here will go out here, right? We'll be adding these things up. So before, when we added these rectangles up, we let the width of the rectangle get close and close to 0. So now we're going to let the angle get closer and closer to 0. So the area of a sector is 1/2 r squared theta, right? So just this sector here would have this length r and this angle theta. So 1/2 r squared theta would be the area of one sector. So I'm going to add up n of these sectors. So I equal 1 to n of these sectors of 1/2 r squared theta, right? And I'll divvy them all up and break them up. We're not going to do it the long way and do a take-home quiz on this or anything like that. I'm going to let this angle get small. So that angle getting small is going to turn into my d theta, and then I'm going to take the limit as n goes to infinity, and you remember that this limit of this sum is what is the integral, right? So the integral of 1/2 r squared d theta. So that's how we're going to find the area bounded in polar coordinates. So just like it was important when we drew the rectangle to find the top and the bottom, we're going to always draw our sectors. The sectors always start from the origin, and then we have to find out which function the sector reaches out to. Okay. So with your graphing calculator, Desmos, however you want to do it, you want to get a picture of what this is. Okay, so I know it's going to be, it's at 0 and 2, and out here at 4, and I just get the picture. I just plot a few points in my head. You can get a calculator. I recognize that it's symmetric with the x-axis. I'm happy. That matches. Okay, so now I want to draw some sectors that show I want to finding the area bounded. So sectors start from the origin, and they look like this, right? So I'm going to have to go all the way around. I'm just going to draw a few of them. This one there's going to go all the way around 0 to 2 pi. So integral 0 to 2 pi of 1/2 r squared d theta. Okay, that's a correct answer. I also could use the symmetry. Can you see from 0 to pi is the same as pi to 2 pi by the nature of the graph? So I could say 2 times 0 to pi, and then have everything else inside the same. And the convenience of that is that the 1/2s and the 2's would cancel, right? Okay. Now let's look at this one. So this is a circle. So this is the circle that just takes 0 to pi to go around. So it's out here at 2, and then here, and then here. So this is a big deal that it's just 0 to pi to go around. So to find the area bounded, the area is 1/2 r squared d theta, and it's just from 0 to pi. Okay, it says to solve this integral. Sometimes I'll say set it up, sometimes I'm going to say solve it. Okay, so let's go solve this one. So this 1/2, and this will be times a 4, right? So this will give me a 2 cosine squared theta d theta. And how do I solve something like this? Yes, you remember, half angle formula to the rescue. All right, so these 2's cancel, so I can take the antiderivative, so I get theta plus 1/2 sine of 2 theta between 0 and pi. So let me bring it up here. So I have theta plus 1/2 sine of 2 theta between 0 and pi. So plug in pi, that gives me plus a 0, right? And then subtract off, plugging in 0, so I just get pi.